Okay, so yeah, good morning everyone or whatever when you watch this video. So I would like to present you, I would like to review this paper about the croissant distribution, and it's gonna be in the in the real life, like no, maybe stochastic probability distribution. And yeah, this our probability density function. It looks complicated, but when we plot it, it looks like this. And you know, uh, we need to cut off here and there using kappa minus and kappa plus. Yes, and when when yeah, and we have the constant equal to 0.42069, which is in the Gaussian exponential here. Yes, and uh, the distribution is this yada 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 yada, and integral we get one. Pretty simple. And yeah, I would like to I would like to introduce author a bit because I know them. The first author is Jin Jin, who is a seven K player, and I think he will take a PhD soon. I don't know when. And Subshu 85, he is studying in applied mathematics masters and get a bachelor degree in statistics. And the last one, evening, also mania player who experiment so many stuff in Osumania, like uh, predicting the performance of the players, and very popular Remember Pi and Alex Zero. Yes. Alright, so we need to find the expected value of the continuous random variable of the Croissant distribution. So let x be a continuous random variable with probability distribution, and we get the formula of expected value of x. This is kind of trivial, and I think I will let this it, as an exercise to the reader, whether it exists, it is well defined. Well, so provide that the integral exists and we evaluate the expected value, it's kind of hard. You need to expand the probability distribution here, and we get a schema T Gaussian exponential and some weird stuff. And the cost to make is squiggling like croissant, and we evaluate the integral and we get this chunk is kind of hard to interpret what does this mean here. But briefly, we get the exponential here, Gaussian exponential, and the the sine and cos function here, and a natural logarithm function. So yeah, the author left the application of this expected value as an exercise to the reader. Yeah, good luck finding a use for this, I guess. And we can find the variance. Well, we're gonna evaluate the variance of the croissant distribution, and we need to record the definition of expected value of the function of continuous random variable, which is written as expected value of gx equal integral of gx if the probability distribution of x from minus infinity to infinity, and everything converges, I think, and the integral actually exists. So I will leave this as an exercise to the reader. And yeah, always remember Blocker and Chin IET. Yeah, and we can introduce the variance of the continuous random variable, which is the integral from minus infinity to infinity of x minus mu squared, and uh, mu is the expected value of x, and multiply things up, and we can simplify the variance as expected value of x squared minus expected value of x squared, and yeah, and we are going to evaluate the expected value of x squared, and we get, yes, the thing here, and is kind of ridiculous to prove better. It is exists, and we might need to use a special function, but anyway, uh, we might try to use a moment generating function, but yeah, it is kind of hard here. Here is a moment generating function, but we use the Wolfram alpha instead because it is easy. You just type the integral in and you get this big chunk of formula for expected value of x squared, and the variance is this chunk of formula, which will, I think, for this we need to use numerical methods to get the integral. It is easier, but yeah, the simplification is left as an exercise to the reader, and we can evaluate the moment generating function as an expected value of tx. So, the second derivative when the n derivative when t equals 0 is the expected value of x to the n. Yeah, and we need to solve for this, and we get this big chunk of formula, which look not good, but we use a Wolfram alpha integration technique, and we get this, and we can find the expected value of x to the n using this formula. And yeah, good luck trying to differentiate this, and the moment generating function of Croissant distribution, and yeah, this thing is just etc expected value of x to the n, and yeah, have fun. But well, I think I should go to the application a bit. I think the application would be for stochastic system, and for the normal distribution that has like the random the noise in this interval, or some sort like that. uh, I think, yeah, it would affect much in the statistics, and yeah, I think that is all. Everything is left as an exercise to a reader. I think there might be the croissant confidence interval and croissant test. I think I need you guys to figure out. Well, I think, yeah, this is all. See ya, everyone.